For this video, I want to work with work problems. So this particular problem right here requires you to understand Hooke's law. If you took physics, then you know what I'm talking about. So the force requires to maintain a string stretches x unit beyond its natural length is proportional to x. So f of x equals to k times x. So K, we call K is a spring constant. So for this particular problem right here, we need to figure out f of x first before we can put in the integral to find work. So what is f of x? Kx in this case. So if the spring stretches from 10 centimeter to 15 centimeter. So if we go from 10 centimeter to 15 centimeter, the amount stretched would be 15 minus 10, right? So that would be 5 centimeter. So it's going to be 0.05 meter. Okay, so what does that mean? That means if you have f of 0.05, the force is going to be 40. Okay, so I need to figure out the function. So based on this, we know that K, we have to figure out for K. So K, 0.05, K is going to be 40 based on Hooke's law. So K, if you take 40, you divide, you're going to get 800. So now we know that f of x is 800x. All right, so that's going to be the function we need to integrate. So the work is going to be 0.05. And then we want to go from 15 to 18. So you go from 0.05 to 0.08. So it's going to be from 10 to 5 and then 10 to 18, right? And we have 800x dx. Okay, so this is the easy part. 800 x squared divided by 2. And then we go from 0.05 to 0.08. So I get 400. And then we go 0.08 square minus 0.05 square. And then it's going to be 1.56. So we're using Newton and meter here. Therefore, we have joule. Okay. So make sure for this problem, make sure you have to convert centimeter to meter. So that's the important part. A lot of people forgot to do that. So for this problem, we want to calculate the work requires to lift the cable to the top of the building. This problem is interesting because we don't have a formula for the force function. Okay, so let's just visualize it. So this is the building. Okay, and I have a cable from the top go down like that. So I have, let's just label, we're gonna label the origin at the top. So that would be the origin. And the cable right here is 100. Okay, because the cable is 100 foot long, hangs vertically from the top of the tall building, right? So, okay, so let's say we divide the cable into small part. So I'm going to divide into small part like that. Okay, and with the length, let's call the length delta x here. Now, if xi right here, x sub I is a point in the I subinterval, then all the points in the interval are lifted by approximately the same amount, namely xi, right? Let's call xi star. Okay, so now the cable weighs 2 pounds per foot. So the weight of the I part is going to be, let's calculate it. It's going to be 2 pounds per foot times delta x feet. Okay, so if we can cancel it out, it's going to be 2 delta x pounds, right? So the work done for I part is going to be 2 delta x pounds. Oh, my bad. Just do 2 delta x because we're talking about force here. 2 delta x times xi star. Okay, so this one is the force. This one is the distance. Okay, so that's what we have. 2xi star delta x. All right, so we get the total work done by adding all of these approximation and let the number of part become so large, right? So we're taking the limit here. So I'm gonna take the work done. I'm gonna write down a limit sum. This is the definition of work. And we've taken care of 2xi star delta x. But what's this? This is going to be the integral from 0 and what is the length? The length is 100. So 0 to 100, 2x dx. So this is just x squared. And then you want to evaluate from 0 to 100, which is 10,000 foot-pounds.